All right, how's it going, people? Welcome to the Office Hour with Dr. Alberto Cruz. I am your host, Dr. Alberto Cruz. The focus of today will be a concept that I like to call functions call other functions. Let's take a look at a main function to see what I'm talking about here. All right, so our first step in this journey of implementing functions at the assembly level, one of the things that you'll notice from your C-level understanding of what a function should do are that if you have some code, such as a main, it can call multiple functions. Another item to note here is that the same function can be called multiple times. So for example, this point and this point, all right? What does this mean? So basically when you hit this instruction, this should jump to the definition of foo, wherever that may be. And the idea is the flow should return back to this instruction, all right? Same thing happens with bar. We call another function called bar. Another example here, we call foo, but one of the things I want to point out to here is that when you call foo this second time, you should still go to the definition of foo, but the point where the flow returns to main is actually different. So here, on that first call to foo, it should return to that first call of foo. On this second call of foo, it should return to that second point, all right? So this leads to an idea that when a function is called, it will not always return to the same point because you can call the same function multiple times in different parts of your code, all right? Let me illustrate now an example where we attempt to implement a function, or at least what we believe to be a function, at the assembly level. All right, people. So with this example, I have a main function that'll start at 0, and it's similar to our C example. It'll call foo, then bar, then foo, and that'll be it for main. All right. Here we've attempted to implement what we would like to see in a C function at the assembly level by using only unconditional branches, all right? Already it's not going to work. Just a couple of notes here. These addresses are arbitrary. I started main at 0. I started foo at 10, noting that each instruction in assembly is 4 bytes long, which is why you see alignment according to 4 bytes here, all right? Anyways, getting back to our example, let's take a look at what foo does. Foo will move a 32-bit value of 0 into the register W0. So I guess it does nothing, really. This is effectively a no-op. But then it should return to main, all right? So this example has a fundamental problem, particularly with the concept of how it handles where it is returning, all right? So if we call this main function and it jumps to foo, so this would mean an unconditional jump, where it sets the flow to go to here because we've labeled that instruction foo at instruction address 10, all right? It performs the no-op, then on instruction 14, it will branch back to main. So this seems like maybe that would work, all right? But what does that mean when this instruction will branch us back to main, all right? Where does that put you? That puts you back at instruction address 0, all right? That would mean, technically, this thing is an infinite loop. You would jump into foo, it would do the no-op, you would jump back into main, and then you would get stuck in main, basically. It would be that same instruction, okay? And well, you might think, hey, maybe I could do main plus 4, Maybe there would be some way that I could specify that it actually has to be the next one. And actually that might make sense, basically. So assuming that we had some ability, which we don't, by the way, to have this thing skip to main plus 4, I guess you could actually label this main plus 4, maybe. Maybe you get away with that. What happens if that happens? Well, so that means it appears to work because you'll jump here, and that's exactly what you want to happen. You'll jump into foo. Main will jump into foo, it'll do the no-op, and then it will execute this instruction, which we believe to be the return, and it will end up at bar. But I want to draw your attention to this next call to foo. All right. Why is that an issue? Well, let's see what happens. So basically, on instruction address 8, it will jump to that point. Okay. It'll still perform the same amount of work as our previous call to foo, but where does this return? If we somehow get it to return to main plus 4, yikes, that actually returns us to bar, which would still cause an infinite loop because you'd be going here and there. All right, so the issue here is that entry into foo is easy enough. You always go to the same point in code where foo is defined, but different points of code may call foo, so the re-entry point, or rather the return, may be different, okay? Let me introduce a new register to you called x30, okay? In various instruction set architectures, this thing is called the return address, that sort of thing. It is used strictly as an instruction pointer to the most current call and its sort of re-entry point when you're done with executing a function, all right? This leads us to another instruction called branch and link, otherwise known as BL, all right? What does BL do? BL is an unconditional branch, just like B, but the difference is it will save the current program counter plus 4 into that register, x30. So what does this do? This basically means it will jump into a function, and this means that basically instead of an unconditional branch to an arbitrary address, you can remember the exact point where the function was called, because that should be placed in x30, basically. All right, well, so that solves the entry point, basically. So let me illustrate what happens here in terms of branching if we change everything to x30. Let's say that this here is x30, and it currently has no value with this code snippet. Let's make a couple of modifications here. What I'm going to do here is I'm going to change all of these to branch and links. BL, BL, BL. All right? You don't need to make any changes to this as of yet, okay? So we have their first call, BL, foo. So on instruction address 0, our main, it will attempt to branch to foo, but a BL is special. It's not like a B, basically. It will unconditionally jump. But the thing that it will do on top of that is to place the PC, which is the current instruction being executed, plus 4 into x30, the register x30. Okay, in fact, you want to think of x30 as the re-entry point into the normal control of flow from the context of the caller, okay? Because we want to return to that address. There's no need now to return to arbitrary points, that sort of thing. So on a branch and link to foo, it jumps into the foo function. We still have our no-op. It doesn't really do anything, right? But the purpose of this example is the flow. So we then hit this instruction, which is B main plus 4. So this one we're going to have to change, right? Because we know that we entered the function on instruction address 0, and we've established that the flow should return to 0x04 on a return from a function call. So that B main plus 4 actually is not sufficient. It cannot be a fixed point that you're returning to. We need to return to that, basically. So enter a new function, which is literally called RET. Okay. RET is similar to a branch, except instead of jumping to a label, it assumes that there is a pointer in a register and you want to jump to that memory address instead. x30, basically. RET is a unary instruction, meaning it only has one argument. So technically you're supposed to put some sort of register here, right? Some sort of X register. But if you omit that, it's implied that X30 will be the return address, all right? So basically you can just write ret, and by the way, branch and link will always place the return address into X30 anyways. So in terms of the scope of this class, I don't actually see why you would need to return to any other register other than X30, basically. So, all right, if you were following that, basically that means instead of writing B main, you will write literally just RET. Remember, RET jumps back to whatever is contained in the register X30, treating that as the next instruction to be executed, all right? So returning to our example now, control is currently at foo. We're done executing our no-op. Then on this instruction, RET, it will take this address and place that into the program counter. All right, what does that mean? Which instruction is for? This one. All right, cool. So that appears to work. Let's check the second function call just to make sure it works for all situations. Let's just skip the bar because I don't want to write the function implementation for bar, all right? Okay, so let's just assume that bar executes appropriately. We hit instruction address 8. I guess you can assume that there's a 12, but in the context of this example, it doesn't really matter, all right? You hit this instruction 8, it branch and links to foo, and then remember, not only does it alter the program counter to jump to wherever foo is located, it clobbers whatever the contents of X30 are, and it replaces it with the PC plus 4. In this instance, this branch and link to foo, located 8 plus 4, should be 12. Actually, should that be 12? That's 8 plus 4 is hex C, right? My bad, people. Edit that out in post. Actually, as you know, I never edit any of that out in post, all right? Okay, so where were we? So basically we were executing address 8. 8 plus 4 is C, so this branch and link will place the value of C into the register X30. Control is now placed inside of foo. It carries out the no-op. And when you hit this return, it doesn't return to any arbitrary point. It returns to whatever the contents of X30 are, which happens to be where we made our function call. All right? So the PC receives the value 0C, meaning that we return to this point, whatever it is. All right? So there you have it, people. We have a little bit of linkage available to us. What I'd like you to do as an exercise before you watch the next video is to see what happens if you have a nested function call like this, and to check what happens with the value of X30. This will motivate our discussion for the stack and why we need to do a bit more to ensure that our function calls are able to return to the appropriate point in the control of flow at any arbitrary point. All right? That's it for today, everybody. Have a great day.